Hello everyone, I'm Carlos Rivas, and today I'll be presenting on enabling return temperature reduction in Austrian district heating systems, absorption heat exchanger integration, and impact analysis. This presentation is part of the Austrian project Absolute, which focuses on integrating absorption heat pumps into district heating and cooling systems. Today, I will highlight the work done in collaboration with my colleagues Farina and Gerald at AEE INTEC alongside SESAAU and WindEnergy on integrating absorption heat pumps into district heating substations. What are we looking at? Well, we aim to replace a traditional district heating system substation, which typically use one or more heat exchangers in parallel, with an absorption heat exchanger. This is essentially an absorption heat pump combined with a heat exchanger. At the right side, we see the return line from the secondary side, the customer side. The mass flow rate is split into two streams. One stream flows through the heat exchanger, while the other goes through the absorption heat pump, first the absorber and then the condenser. The two streams merge to supply the customer at the required temperature, in this case 85 degrees. At the left side, we have that the high temperature primary line drives the absorption heat pump. First, it passes through the generator, it cools down, then moves through the heat exchanger, exiting at the temperature above the secondary return, in this exemplary case 47 degrees, and afterwards it passes through the evaporator, further reducing the temperature, reaching about 32 degrees in this case. This is the effect that we are seeking, the subcooling effect, where we achieve a temperature reduction at the primary side of the return line below the temperature of the return line of the secondary side. Notice that in the regular heat exchanger, this temperature would be above 47 degrees, specifically 51 degrees for an effectiveness of 95%. Well, why are we doing that? Well, lowering the temperature on the primary side leads to several advantages or benefits. One of them is the increased transport capacity. We are having a higher temperature spread on the primary side, the temperature difference between supply and return. It leads to a principal lower mass flow rate, so we could increase it again to gain this transport capacity to use it to supply our customers. Otherwise, we would have a reduced pumping cost because in this reduction of mass flow rate, reduced heat losses, and in some cases might be an increase of efficiency. For instance, in the case there are solar thermal installations present. Well, before going into the results, just a short overview about the workflow we have following the project. There has been done some laboratory work. We set up absorption heat exchanger. We tested at the lab. As I mentioned, there are two references you can have a look. A master thesis from Damian and a publication in the heat pump conference from Gerald Soto. There is then, from my side, the development of absorption heat exchanger modelica model, which I validate against measured data. And then we upscale this model to represent a substation of the size, the typical size in Vienna, which in this case was about almost 3 megawatts. And I did so with the support of the project partner Steps Ahead. And finally, we carry out some different simulation studies for different scenarios to assess the impact of the absorption heat exchanger. Well, for the validation work, we use data from several experiments, the ones I mentioned before that we have done in the lab. And here, just to mention that we have a volume flow rate. These are used as input variables for the model. And we also use, of course, the temperatures entering, in this case, the generator and also the absorber, let's say primary and secondary side. For the validation, we look at the temperatures mainly temperatures leaving the main heat exchangers, the condenser, evaporator, and so on. Well, for today's presentation, I just have a very short one slide about the validation results. This is to show, for instance, the outlet temperature at the evaporator. It was a 14 hours period what we are looking at. The orange line is the measurement done at the lab, and the blue line are the simulation results. Okay, we have a good agreement between these two. I have to say that there is a deviation of 1 to 2 degrees on the first part of the experiment, where the entering temperature, this would be the return line of the secondary side from the customers, it's about 38 degrees. Here we have this underestimation of the temperature, the living temperature at the evaporator. And then the second part of the experiment, where this temperature was increased to 55 degrees, we have a slightly overestimation, where the living temperature at the evaporator for the simulation is slightly higher than the measured values at the laboratory. Well, as I mentioned before, we took the validated model and we upscaled it with help of the project partner Steps Ahead to a 2.8 megawatt district heating substation. And to carry out the simulation studies, we did similarly to the validation work. What we did was use measure data as an input data. In this case, the driving temperature, the inlet temperature of the primary side. Again, the inlet temperature from the secondary side, as well as the mass flow rate. And when we also use the supply temperature of the secondary side as a target value to control the mass flow rate of the primary side. So we regulate the mass flow here at the primary side to ensure the set point is achieved. And for the evaluation, of course, we look at the living temperature at the evaporator, which is the return line of the primary side. On this slide, we present the main results of our simulation. The black line represents the return temperature of the primary site in the original setup without absorption heat exchanger. The blue line shows the return temperature when the absorption heat exchanger is implemented. The key benefit is evident from the difference between the two temperatures. The absorption heat exchanger can reduce the return temperature on the primary side significantly. The temperature reduction is in the range of 6 to 29 degrees, 17 in average. And this temperature reduction leads to roughly a 20% decrease in the primary side mass flow rate. This reduction in mass flow rate has important implications. It allows for the connection of additional customers, thus increasing the transport capacity of the district heating network. Finally mentioned, WindEnergy has conducted some economic evaluation of the absorption heat exchanger implementation, which has positive results, but I'm not able to provide the specifics about it. Although the absorption heat exchanger concept has been positively evaluated, there are several challenges that are currently slowing down the realization of a pilot project. Most important one are the space requirements. The absorption heat pump requires additionally about 15 square meters of space, and finding existing district heating substations with sufficient room for this addition is a challenge for us now. There is also increased investment and complexity, which requires training personnel to operate and maintain the new type of substations. Also, the primary side will experience a higher pressure drop as the mass flow rate passes through 3 heat exchangers instead of 1. This must be carefully considered during the planning phase. And also, due to limited experience with this technology, there are concerns regarding the supply reliability. This slide presents a benchmark diagram to help evaluate the benefits of integrating an absorption heat exchanger into a district heating system. The specific advantages, such as reduction in heat losses or increased transport capacity, etc., vary depending on the characteristics of each district heating network, so operators will need to perform their own assessment. The diagram shows the subcooling effect on the vertical axis as a function of the driving temperature, T11. Subcooling is defined as the temperature difference between the secondary side, T22, and the temperature at the primary side, T12, leaving the evaporator. The diagram includes our own results, represented by the black line, as well as data from other projects. Each dataset is labeled with the source and the range of secondary side supply and return temperatures, allowing for a comparative analysis of subcooling across different scenarios. To conclude, here are the key takeaways from the presentation. The absorption heat exchanger can effectively reduce the return temperature on the primary side thanks to the subcooling effect at the evaporator. The absorption heat exchanger is a viable alternative and complementary solution to other approaches such as tariff incentives or upgrading customers' heating systems. The benefits and effectiveness of the absorption heat exchanger are highly case dependent and need to be evaluated independently for every project. For instance, the degree of subcooling achieved is influenced by various factors such as driving temperature or secondary side temperatures. A preliminary estimation can be made using literature values and tools like the benchmark diagram shown in the previous slide. Finally, increased space need for the absorption heat exchanger, particularly in existing district heating substations, poses a significant challenge. There is a clear need for more compact designs to address this issue. Thank you for your attention. I'm very happy to take any questions you might have.